So plowing along through the transmission line equations, this is more or less where we left off, where we had derived these two equations down here, which are coupled in terms of current and voltage at that point x, or actually any point along that line. So what we can do with these equations, let's say you take that first one, you differentiate it with respect to x, you get something that looks like this. And then you take the second equation and do a simple substitution in for here, so we get this equation down at the bottom. Take that second equation again, differentiate it with respect to x, and or with respect to t rather, and end up with this expression down here, and we substitute that back into 1, and what we're left with is the wave equation here, and we'll see that's only in terms of v. Obviously, whoever derived that the first time probably tried a few more little trial and error things before they got to there, but anyway, it became known as the wave equation. It's certainly not new. It's been around since the 1880s or so. Probably derived by Maxwell or certainly one of his contemporaries. And in any event, for the lossless transmission line, we have r is that equal to 0, so one of those terms is going to drop out, and we're left with a slightly more simple equation. And Maxwell also noted that this v squared down here is the velocity squared, and it can be then, since it's basically the same as 1 over this thing, it can be related to the parameters associated with the line, like the inductance and conductance per unit length, which can then be related to some material properties and geometry, and as a consequence it's related to the speed of light in a vacuum divided by the square root of the relative permeability and relative permittivity. So for silicon dioxide, for example, if that's the insulating layer, it's about 4, and the permeability is about 1, so the velocity of the propagation of a signal along that transmission line would be c by 2. And this is what we'd used previously, and it's useful certainly for the time of flight calculations, because using that velocity and knowing how long the line is, we know how long it takes for the signal to get from one end to the other. So for the lossless transmission line, we're going to look at a case here where this G is 0 and that R is 0, so just left with this inductor and this capacitor. Again, it's divided up into these incremental pieces, and we saw the governing equations for it. But in any event, what we're going to do here is we're going to apply a voltage step to the end of the transmission line. So basically this step will travel with velocity v, which we already know the expression for v, which roughly then would be the speed of light divided by 2. At some point x, the voltage is v to the left completely, so let's say to this point in time the voltage would be v, and on this side of x the voltage would be 0. Basically it hadn't propagated at that point yet. So the c dx here, which is the capacitance sitting down here on this little incremental piece, must be charged to the voltage v to get a voltage v an additional delta x along the wire. So we know what that charge is. It's the capacitance times the voltage. So that was the c dx times v, and that's basically the change in charge. So if we look at the change in charge with respect to time, that's the current, we're left with that expression again. This is c dx, that was that incremental bit of capacitance. This was the voltage that we charged up that capacitor to, and we differentiate with respect to time, just rearranging slightly, and we get c times the voltage with dx dt. And dx dt is velocity, and Maxwell already solved that for us and told us it's 1 over root LC, or this expression down here. In any event, we can write I is equal to the capacitance per unit length times the voltage times the velocity. We know what the velocity is in terms of 1 over root LC, and this c will cancel that root there, and we end up with a simple expression between current and voltage. And since we have that simple relationship, and we know that V divided by I is equal to a resistance, it becomes this characteristic impedance. And that characteristic impedance, if we do a little bit of algebra, comes out to the square root of L over C. And this is sort of what at least one of the schematics that I found makes it look like. Here's the current going down the line at that point in time. This is the return path. Here's the current going that way. And this is the voltage. I think it's the voltage more properly across here, but could be wrong. And that would be definitely the direction of propagation. So that would be the wire, and that would be the substrate or ground return. So that characteristic impedance of the line is a function of the dielectric medium and the geometry of the wire and dielectric. If a line were terminated in that characteristic impedance, it would in effect look like it was infinite at length. I mean, the signal propagating down that line you wouldn't realize that it had come to a termination if it's terminated in the characteristic impedance of the line. So a signal would never know where the end was effectively, so you get no reflection. So in that case, the goal might be to match the impedance at the receiving end. Often that's the case certainly for power systems, but may not be necessarily the case here. Z0, that's the characteristic impedance. It's in ohms. That's the, how we derived it earlier. It was just from V equals IR. And for example, metal in an integrated circuit, that might be on the order of 10 to 200 ohms. So here's a real transmission line with some termination. It's certainly strongly influenced by the termination of the line. That's both at the destination as well as the source. And basically this termination will tell us how much of the wave is reflected back at the end of the wire. And that's a consequence called the reflection coefficient. Can't recall the exact derivation for it, but it's something like this. At the end of the line there, the voltage divided by the current is equal to the impedance seen at the load. And for the solution of these types of equations, they're traveling waves. So one is an incident wave, one's a reflected wave. That's the voltage. And the current is the incident voltage minus the reflected current. So this thing here is this again re-expressed in terms of the characteristic impedance, and we're going to see then that from here it's relatively straightforward for us to calculate the reflection coefficient, and this is what it happens to be. Say at the load end it's ZL minus Z0 divided by ZL plus Z0. So this reflection coefficient clearly can be anywhere in the regime from -1 to 1. And this would again apply for the source end as well if we're looking back from the load back toward the source. So here's a couple of interesting T-line terminations. In this particular case, the load was equal to the characteristic impedance of the transmission line. So when there's a voltage applied here, it's going to march on down that transmission line, and when it gets to the end, it's matched, so there's no reflection there, and the load would just see the voltage V across it. Another case that's interesting is an open circuit, and in this particular case, voltage will march down the transmission line. It'll hit the end of the line, and it'll be totally reflected. If we went back and looked at a reflection coefficient from the previous slide, we'd see that if this is infinite, then the reflection coefficient is equal to 1. So we're left with the incident wave being reflected. It's added there, and the voltage is doubled, and it starts heading back toward the source. The other interesting case is if the load is short-circuited, in which case then the voltage will march down the transmission line. At the far end, it'll see a reflection coefficient of -1, and at that point in time, the voltage is reflected. It's negative and opposite. It'll head back the opposite direction, and the voltage at the end of that line would be the sum here, which would be 0, which we'd expect because it's a short circuit. So an in-class assignment for the transmission line parts would be which of these resembles a CMOS termination, or perhaps which of these more closely resembles a CMOS termination. Other things to bear in mind while we're looking at this is, the real interconnects are going to be a little bit messier, and as a consequence we might end up with, let's say, trying to launch a signal down this wire here, and it's going to be delayed by the buffer itself. We'll have to take into account the time of flight, as well as perhaps some oscillation or ringing at the end of the transmission line. And there could also have been a mismatch here, which could have caused this a problem. But in any event, this disparity can arise in timing, and a consequence of the fact that these two wires are of different length, so the times of flight are different. And that's perhaps kind of obvious. At this point in time, we'll take another break.